equilibrium. Balance forces should have, and those are similar, I can see why you would get them confused. Balance forces should have been O, the state in which the individual forces entirely counteract one another. And then equilibrium, number 7, should have been N, which is the state assumed in which all of the individual forces are balanced. Also, some people switched Galileo and Newton. Galileo was actually the one that developed the concept of inertia, and Newton just built upon his thoughts about that. Are there any other questions about those multiple choice in front? I think those were the main things. Okay. And then
That's on this part there.
I counted each of these. 16 through 25 was 2 points, which is why some of you missed like fractional points, because it was 1 point for having the right answer and 1 point for having the right forces. As long as you had the same number of forces as were in that diagram and they made sense, I counted it right. So like, if there's 4 arrows on the net force diagram that you picked for that one, there should be 4 forces, right? So, like for number I, it's kind of a judgment call whether you say that force is friction or air resistance. But let's just go through those. 16 should have been H, because I think everybody got that one actually. Because it's a constant velocity, the forces would be balanced, and so the arrows are the same, and it does tell you to consider air resistance, and the other force would be gravity. So 16 is H, and the forces are gravity and air resistance. 17 is C. Again, it says constant velocity, so that's another one where all the forces should be balanced. And so you should have 4 forces: gravity, normal, friction, and applied. 18 is one that a lot of people missed. It was supposed to be I. Because it says the wheels are locked, there's not an applied force. It's moving to the right, so the friction would be moving to the left, or again, if you wanted to say air resistance instead of friction, I would be okay with that. And then you have the gravity force and the normal force. So you should have had 3. I said gravity, normal, and friction, and that would have been I for number 18. Questions about that? Does that make sense? Okay. 19 is another one I think that got switched. Was D. Again, the baseball player is slowing down, so there's only 3 forces. There's gravity, the normal, and the friction. He's moving to the left, so the friction would be to the right. And 20 is F, because it says he's moving rightwards and speeding up, but he is also encountering significant air resistance. So there's gravity, normal, air resistance, and also the applied force of like his gas pedal, or however he's continuing to move to the right. 21 is G. I think most of you got G for that. Gravity and air resistance. 22 is J, also gravity and air resistance. 23 is A, gravity. 24 is E, and 25 is B, gravity, normal, friction, and applied. Okay? Questions? Okay. And then for the net force was 2 points for each one, 1 point for having the right net force, and the second point for having the direction. So remember, force is a vector quantity, so you need to have the number and then also the direction that it's going. So 26 is 0 newtons, so there would be no direction for 0. 27 would be 10 newtons right. 28 would be 20 newtons right, 29 would be 35 newtons right, and 30 would be 20 newtons left. Okay?
What? Well, at least you understand. I know. Good point, though. Do you need feedback?
Yes, please. Any questions? No? Okay, then we're
That is fun.
wow, you guys are pretty good.
I got a high in my state at 94.
Okay, so we're going to talk about the second law of motion.
Whatever goes up must be down.
What does say that? I guess that, maybe that's actually the third law that talks about gravity. I think it is part of the
I don't know, I was
law.
just danger.
We're gonna watch a video. It's not quite as good as the other one. I couldn't find a really good second one.
Can I actually just grab my notebook?
We shall soon find out.
But on your creation. Now. We can guess.
What do you think?
Does it have to do with gravity?
No, that is the third law.
Does it have to do with friction?
Not really.
Does it have to do?
I hate that these pants.
Does it have to do with normal force?
Somewhat. It has to do with net force,
Oh.
maybe.
I usually wrap mine around this.
And unbalanced.
I know, honey.
Can you guys see that right now? Yes?
His face is like,
Oh, it stopped playing.
Come take a look at this.
oh, that was torturous. My skin is strong in there.
Actually, there are things, right?
Sir Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there, but this one is heavier, and you're going to have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now what I'm going to do is I'm going to try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm going to put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and... Could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. McMillan Space Center, I'm Cam Cronin. Thanks again, Parnelli.
That was a little funny.
You like videotape the guy.
The
for like
McMillan
10
Center is
seconds.
really cool. I've been to it.
Oh, yeah. I don't know if that's the same thing, but it is. Alright, let's
Because
do.
that was my current.
Well, I used to live in
Oh,
California. Yeah.
so that's not the one that I'm thinking. You're thinking of the real one. I'm not thinking. Alright, go ahead and get out your notes. So Newton's second law. What did you guys get from the video to summarize the second law?
That the lighter the object is, the easier it is to push.
Right.
Or the less force you need to push it.
Right, good. Okay, in actual words,
Yeah,
It's-
sorry.
no, paraphrasing is better, I think you understand it better that way, but this is what it actually says. The acceleration produced by net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So the part that you're saying, Holly, is the second part where it says it's inversely proportional to the mass of the object, meaning the heavier the object is, the less acceleration it will be produced. But the first part of it, when it's talking about the net force is directly proportional to the acceleration, so the higher the net force, the higher the acceleration. Okay, so for the first law, we were talking about when forces are balanced, and we started talking about what happens when forces are unbalanced, and that's what Newton's second law has to deal with. So we kind of had a flow chart last time, and we'll do that again. So this time we have forces that are unbalanced, and there's two things that we know. First of all, there is always an acceleration when the forces are unbalanced. And then if there's an acceleration, the acceleration depends directly on the net force. I'm having formatting issues here. It'll depend directly on the net force. And then we also know that the acceleration depends inversely on the object's mass. Ah. Okay. So when forces are balanced, there is an acceleration. The acceleration depends directly on the net force and inversely on the object's mass. Kind of an easier way to say that is as the net force increases or goes up, the acceleration goes up. Or increases. And this is saying as the mass increases, the acceleration decreases. So from this, we can actually get an equation. In equation form, the second law says that acceleration equals the net force divided by the mass, or oftentimes we write that as the net force equals mass times acceleration. Okay. Alright, so let's do some questions. Alright, first of all, if you look at this table, based on that formula, what would the acceleration be in case 1? 5. How did you get 5? 10 divided by 2. Good, because net force divided by mass equals acceleration, or mass times acceleration equals net force. What would be the acceleration in case 2?
10.
Good. 3.
5.
Good. What's the net force in case 4?
20.
Good. And the mass for case 5?
4.
What?
1.
Good. Okay. Very good. So we can use Newton's second law based on mass and acceleration to calculate net force, or to figure out any of those unknown variables if we have 2 of them. Good. Which of the following can be explained using Newton's second law of motion? Does it explain why a moving object keeps the same velocity? Why every force is accompanied by a reaction force? Or why an object accelerates with a particular acceleration value?
C.
Good. The acceleration of an object is blank proportional to the net force and blank proportional to its mass.
C.
Good. So directly proportional to the net force means as the net force goes up, the acceleration goes up. Inversely, as mass goes up, acceleration goes down. Okay, an object has an acceleration of 12 meters per second per second. The net force acting on the object is doubled while the mass of the object is held constant. What will be the new acceleration? Right now the acceleration is 12. If it's directly proportional to the net force and the mass is not changing and the net force is doubled, what should happen to the acceleration? It should also double. So it would be E. Good. Does that make sense? Okay, an object has an acceleration of 12, the mass is doubled, while the net force is held constant. What will be the new acceleration? So that's like the opposite of that.
Speed.
What?
Speeds.
6? Good, why did you choose speed?
Because the mass went up, so it has to decrease.
Right, so if it's inversely proportional and the mass doubles, then we would divide it by 2 to get the acceleration. Good. An object has an acceleration of 12, the net force is doubled, and the mass is halved. What will be the new acceleration?
Is it B?
See why you would think that. Is it B?
Is it D? Is it
It's
D? Can you like write out the equation?
Okay, so the acceleration,
Writing.
well, acceleration equals net force times mass. If the acceleration is 12 and the net force is doubled, and the mass is halved.
Oh, I took I multiplied 12 times 2 and then I divided it by 2 and that's why I got B.
Right, but since it has the inverse relationship of mass, so if the net force doubles, what happens to the acceleration?
Double.
It doubles. So it'll multiply by 2 because the net force is doubling. And then if the mass is halved, what's the inverse or the opposite of having something? Having it by 2. So really, we're multiplying 12 times 2 times 2, 12 times 4, which is where the 48 comes from. The mass and acceleration, can you guys see that? Okay. Of 3 objects is shown. The acceleration is represented by an arrow. Rank the objects in order from the least to the greatest net force. So, how would you calculate the net force if you know acceleration and mass?
Mass times acceleration.
Mass
Divided by acceleration. No.
Times acceleration.
How do you isolate the net force in that equation?
I was using a different equation. I was using the F net equals mass times acceleration.
Okay. Either way, you should get... Actually, that one isn't right. That one should be divided by... Right. Which is why we multiplied by them. Sorry. So how do we isolate the net force?
Multiply mass and acceleration.
Right. So
It's B.
which order would it go? Good. A is less than C is less than B, so A then B then C. So the arrows are not the scale, I guess. The mass of and net force is shown. Rank the objects from the least to the greatest acceleration. So how do we, well, there's acceleration. It's net force divided by mass. I apologize, I wrote that down wrong earlier.
Number C.
No.
C is the littlest. Oh wait, no, wait, 2 divided by 4. That's 1/2. And then 4, and then I don't know what each
One
is.
is
It's
D,
too much
one is
math.
D.
It's a fraction.
Oh, no, it's C. Hooray.
Yes. C is the smallest because to get the acceleration we divide the net force by the mass, so that would be 1/2. B would be 3 and A would be 4. Okay. A rightward force of 30 newtons is applied to a 5 kilogram object to accelerate it across a horizontal surface. The object encounters 20 newtons of friction. What are the net force and the acceleration values? So first of all, you have to calculate what the net force would be. Because there's a rightward force of 30 and 20 of friction. What would the net force be?
10.
Okay, and then what would the acceleration be?
It'd be 2.
So, okay. Okay, number 9, a rightward force of 40 is applied to a 5 kilogram object to accelerate it across the horizontal surface. The object encounters 10 newtons of friction. What are the net force and acceleration? Good. Does everyone see where that's coming from? Yes.
The acceleration, because you get like the net force of 30 and then you divide that by what?
The weight,
Oh, okay.
or the mass, sorry.
Yeah.
Okay, good. Last one. If 1 newton is defined as the amount of force that gives 1 kilogram of mass and acceleration of 1 meter per second, then what is 1 newton per kilogram equal to?
B?
Very
That's what I was laughing at. B? Very good. Okay. We still have time to go, but I have some practice. Printer will start. There we go. Okay.